Let's start. So people from the people who have attended the first part of it, you don't have to download anything new. It's in the same repo. It's the 7th and 8th notebook. So before we start, how many of you weren't there in the first part? Okay. How many of you who weren't there in the first part have attended a previous tutorial by Eric in PyCon, SciPy, or PyDit or anything? Okay, so you don't know this material, right? Okay. So we'll take that into account. Yep. So in the first, okay, so the people who were there in the first tutorial, the majority of the people were there in the first tutorial. So in the first part, we saw different types of, like, introduction to network X, and different types of ways of working with them. Like some type of algorithm, some types of statistics to work with networks. And this, we're gonna look at 2 different data sets. One is Game of Thrones, yay. The other is US airports, again, yay. And so we're gonna use network analysis and the things that we went through in the first part, and work with some real world data set and see why what we did in the first part is useful. So people who like Game of Thrones, people who don't like Game of Thrones, people who don't care about Game of Thrones. Very good. Okay, people who are not familiar with Game of Thrones, who have never heard. Oh, what? Okay. So, for the people who don't know what Game of Thrones is, it's a TV show based on a set of books, and it's just another fantasy-filled novel / TV show. So, what we have here is we have a character interaction network, and how did we end up with that? So the people who made this network, they passed the books. This is based on the books, not the TV show. They passed the books, and if there are 2 characters which have which are in proximity of like 15 words, they have a link between them. This is not the best way of making it, but this is one way of doing it. So, and they did some fancy analysis, and they ended up with this picture. Can people who are familiar with Game of Thrones, does this make sense, this picture? And people who were there in the first part, can you try to, what is this picture about? Just without reading the description. So the network is just made by the interactions. That's all. The edge between, for example, John and Rob is there only because there is some interaction between them. That's all. There is no dialogue or chapter wise. It's just. What do you count as interaction? So for this, what they did was, suppose if the word Jon Snow and Rob Stark comes in like 15 words of each other, that's an interaction. As I said earlier, this is not the best way of doing it, but it's a way of doing it. Yes, unfortunately, yes. And then there are other like caveats with this, like suppose you're talking about the king, the queen. Which king? Which queen? But luckily for us, the people who made this network, they kind of did some manual things too. So they have taken that into account. So by the end of this notebook, we're going to understand what's happening here. And so as a starter, bigger the name of bigger the font in this network, the more important the node is in the network. And as we saw in the earlier part, there are different ways of measuring importance. There is degree centrality, there is betweenness centrality. In this, it's page rank. People who are familiar with page rank. Yep, so it's known as the billion-dollar algorithm because that was the initial algorithm that Google used to rank web pages on index web pages and give them ranking, which is more important. And the color in this is communities. You can see that Jon Snow has this community of Samwell, Mains. Then Rob has his community of Catelyn, the Starks. Then you have Tyrion with the Lannisters. So I mean, it kind of makes sense. So let's start. Oh, okay, so people who weren't there in the first part. So this is how we're gonna work. In your repository, you have two type of notebooks. One is student notebook, one is instructor notebook. So we're gonna do 7 Game of Thrones student and 7 Game of Thrones instructor. I'm gonna go through the instructor one. It has all the solutions already, and you're gonna if you want to code up the solution, and if you want to do exercises, which I recommend, you should do the student one. So yep. So is everyone set up? Everyone has this cell running. You can try running this cell. Does it throw any error? If you are done, please raise your hand. Yeah, perfect. So let's load in the data sets. These are CSV files. You just have to, the code is there for you, you just have to press Shift Enter. And so let's look at what's there in this data set. So, and it's based on books, so we have the first 5 books right now. And we load in the 5 books, and let's see what's there in a book. So you see it's a pandas data frame with source, target, type, weight, and book. Like source is source and target are the 2 edges, are the 2 nodes between which we have an edge, and this is an undirected network. So you have type undirected for everything. So it doesn't that column doesn't really matter in this one, and the word source and target also doesn't make sense because if X is a source for Y, then in an undirected network, Y is a source for X2. And weight is the number of interactions you have. So suppose if the weight is 6, it means that there were 6 these interactions between Adam Marbrand and Tywin Lannister. And we're gonna see why this matters. Let's move forward. So we're gonna create 5 graphs. We can create one graph too, which is basically a multi-graph, and it's every edge represents another book, but it's not that easy to play around with, and we're gonna see why in the next notebook, where we're going to make a multi-directed graph. So let's just populate the network now. And to make our lives easier, we have created this variable books, which is basically a list of all these books, graphs of books. So let's see what it looks like. So you have one edge in book 1, which is between Jaime Lannister and Loras Tyrell, which has a weight 3. So just a basic exploration of what the data set is. And then there's between Benjen Stark and Theon Greyjoy in book 4. So in book 1, if you want to see a book 5, you have an interaction between Daenerys Targaryen and Gael with a weight 5. So let's find the most important node in this network. Is it Jon Snow? Is it Daenerys Targaryen? Is it, I don't know. Let's see. According to mathematics, not according to storytelling, but let's see what maths and network science can tell us about this. So we're going to start with the most basic one, that is degree centrality. And people who weren't there in the first part of this, degree centrality is basically measuring the number of neighbors that a node has. So for for example, like if you have a Twitter network, then the number of followers of a person is, it's kind of, it's not exactly its degree, it's his in degree, but let's say it's his degree, which is the number of followers it has. So that, and if you normalize it by the total number of nodes minus one in that, that's called degree centrality, which is just a fancy way of saying degree. So let's see what degree centrality tells us. So and we do this for, like, different books just to check it out, how things are changing between book 1, book 2, book 3, book 4, book 5. As you can see, we did this for book 1, and we see Eddard Stark is the most important character in book 1, according to degree centrality. Let's see what happens to Eddard Stark in book 2. We don't have a book 2 yet. But yep. So in book 2, we don't see Eddard Stark even in the top 10. So something happened there. I'm not sure what, but something happened. And like, if you are behind on Game of Thrones, I've tried my hard of not including any spoilers, but people will laugh. That's on them, not me. So again, once we know the most important character in books, according to degree centrality, we have Eddard Stark. Then we have Tyrion Lannister in the second book. In the 5th book, we have Jon Snow and Daenerys Targaryen and Stannis Baratheon. You can kind of see that things change. The Starks were important, maybe not anymore, as you go from book 1 to book 5. Okay, and I see a lot of faces that are lost. If you don't follow Game of Thrones, I'm sorry, but just think of it as like some random characters with interesting backstories. So once we have a network, one of the most interesting part of is the degree centrality distribution, as Eric talked about in the last part. He doesn't really like histograms, but it's the most, I think, for me, I like it because it kind of it's gonna help it's gonna help the point that I'm going to make. So this is the distribution of degree centrality, or degree, we can use this interchangeably. You see that most of the nodes in this network are not connected to a lot of other people. You have let's remove centrality. Yes, most of the nodes in this network are not really connected to a lot of people, and this kind of makes sense. Going back to the Twitter example, not everyone is followed by millions of people. You have bunch of people who are followed by millions of people, but most of them, like me, are followed by 300 people. But that's the end of it. And you can see this, something like this. So this thing is called power law. I'm not sure if it's kind of a distribution, and so this kind of follows that. And if we did this for every network that we encountered in the first part, every real world network we encountered in the first part, we would have ended up with something like this, a distribution like this. So okay, let's just take a detour. We are talking about distributions, and I like these distributions. So when you want to create a synthetic data set, one of the first thing is you want to create a random data set, right? How do you create a random data set? So this was a very early model, which is called Erdős-Rényi model. So suppose you want a data set with 10 nodes and with a density of 0.2. And let's just draw it out. So you'll end up with something like this. This is a network with 10 nodes and a density of 0.2. And suppose if you make it 1, you'll have a full network, which is everything is connected to each other, because the density is 1. And if we make it 0, it's just a bunch of nodes not connected to any other. So this is, I think this was proposed in mid 70s, if I'm not wrong, like way before 80s. It was proposed in 60s or 70s by Eldos, this famous dude who used to go around everywhere in the world to work with people, and by Rennie. So they came up with this model, and they thought, like a lot of people thought till 20, 30 years, that if you want to make synthetic data for network, this should work. This should represent real world networks. But for example, even in this fantasy real world network, it's not that simple. So okay, let me show you another picture to explain this better. If we plot the degree centrality of this, if we plot the histogram of this, we're gonna we're gonna end up with something like this. Okay, this is not a good representation. So let's make it more nodes. Let's make it like 1,000 nodes. So we end up with something like this, and it peaks around 0.3, which is our density. And if we change the density, it's going to peak at that density. So just by looking at degrees and the degree distribution, these are fundamentally different networks. You cannot say that if you want a synthetic data set, I'm going to create an Erdos-Rennie graph and use this on my algorithms to test out will it work on real world data sets or not. And we need this because suppose you want to work on a social networking problem, and Facebook is not going to give you the data, like present news excluded, but it's not going to give you the data to work around with it. So you want to create your own synthetic data, right? So this is not the best way of doing it. So in late 90s, these two scientists called Barabasi and Albert, they came up with another model, and NetworkX has that too, which is called, surprise, surprise, Barabasi-Albert model. And if suppose we create a 100 node with a coefficient of 6, I'm not going to tell you what that is, but let's just see. We see a different distribution now. These two are very different distributions. To get a better idea, let's do 4,000. Now it's kind of getting to this, which is a real world network, and this is our model of network. And this is a randomly generated model. So, I mean, this when this was proposed, this was considered as like whoa, we have found the answer of this. But this year in January, there was an interesting article on this, that how all real world networks they don't follow power law. It's considered that they do. It was considered for like 20 years that, okay, like we have this BA model, Barabasi-Albert model, everything works for this. But when they tested out with real world data sets, they tested out with like 1,000 real world networks, and only 4% of them actually followed this model. But like there's a lot of debate going on in the network science community. It's does it follow or does it not follow? We're not going to go into that. So this is another way of plotting the same thing. Instead of plotting the histogram, in this I'm plotting the log plot of the histogram, the normal log, and if it's a perfect power law, it should follow a straight line, and you can see it's kind of following a straight line. So again, it's not the perfect representation, but it is something. So time for exercise, the first exercise. We had this term called weight, right? And when we calculate degree centrality, we just look at the number of nodes it's connected to, that's all. But we have this new information called weight, which like, how many times did the network, did the character A interact with character B? So let's use that information, and we create a new measure that's called weighted degree centrality, or just weighted degree. It's just weighted degree, not centrality. Weighted degree, in which you have to take in a graph, and the weight you have taken a graph and the weight attribute of the graph, and you have to return the weighted degree of that graph for every node. You have, I guess, 5 minutes for that. And as Eric said, noise. Yes. And once you're done with it, you should also plot it out, the distribution of this, and if you are getting something like this, then that's, I guess, right. And once you are done, thumbs up. People who have this histogram. Again, this is one of the possible answers. It's very much possible that you can write a nice, neat comprehension to do the same thing. Okay, so let's go through the answer. In this, we create an empty dictionary for storing our result, and we traverse all the nodes. And so basically, the basic idea is we basically add all the weights for a node which are in its neighborhood, and we end up with something like this. And this is our plot. So again, this kind of follows power law. I'm not saying it's signifying anything, but I'm just saying it kind of follows power law. And so let's see, does this make any difference to our importance measures? So let's run sorted weighted degree, and we see that Jon Snow is this for book 1, and Jon Snow is the third most important person in this network. and it was earlier the fifth most important when we didn't take weights into consideration. So it's pumping up Johnson. So maybe it's a good measure. Maybe. So again, degree centrality is like one of the most basic ones. So let's see if we find any interesting stuff if we look at other centrality measures. And again, like before we do this, there is no correct centrality measure. There's no one right. If you want that degree centrality is better, flow centrality is better, betweenness, no, that's not like it. It pretty much depends what you want to get out of the data, and that's like every metric means something different. So you need to know that. So if we do betweenness centrality for book 1, we see that again Eddard Stark is the most important one. So like we have two different methods which takes in very different ideas behind them. One is just counting the number of nodes, and the other is counting the number of shortest path that goes through that node, and both of them tell us it's Eddard Stark. So maybe, just maybe, Eddard Stark is important in book 1. Okay, networks tell us that, and you have Robert Baratheon and Tyrion Lannister. So it's pretty much similar to the degree centrality one. So maybe these are actually important nodes in the network. So, and again, right now this is unweighted. So like right now this is unweighted, so we haven't taken weight into account. Let's see if taking weight into account make a difference, and it makes a difference. Now Robert Baratheon is the most important one if you take into account weights, and yep. So again, we have seen degree centrality, we have seen betweenness centrality. Now let's talk about page rank. So as I said, the billion dollar algorithm. Let's see what it can tell us about Game of Thrones. So again, even PageRank tells us that Eddard Stark is the most important one. So maybe I think we can safely conclude that Eddard Stark is the most important node in the first book, and the most important character in the first book. And again, we take the weighted one and the unweighted one. Again, Eddard Stark. So I guess now it's safe to say that Eddard Stark is important in first book. But so okay, let's see if there's a correlation between these techniques. These three techniques use very different ideas behind them. But do we find any correlation? This is an exercise. So people who are comfortable with pandas will find it kind of easy. So, and you have 5 minutes for this too. Once you are done, Did anyone end up with this correlation matrix? Can someone explain me what's happening here when we do this? Anyone? So what we are doing here is we create a data, like this is the laziest way of doing this, finding the correlation, but it like there are probably other ways and maybe better ways, but this is the laziest way of doing it. So we create a data frame, aggregated data frame for all the for all the different measures, which is keyed in by where the column name is the character, and we can use the inbuilt correlation function, which gives you the Pearson correlation coefficient, and if we look at it, 0 and 2 have a correlation of 0.99, and 0 and 2 is page rank and weighted degree. That's very weird and interesting. I mean, and 0 and 3 too. So degree and page rank also have a nice correlation. So maybe in this network, degree and page rank are kind of correlated. So till now we were talking about book 1, book 2, like individual books. Now, what's the interesting part of this is that if someone is important in book 1, things happen, then book 2 comes out. Nature has this way of letting things die. So let's see how it's evolving. So let's just pick 3 characters right now, like Eddard Stark, Tyrion, and Jon Snow. Like these are people who don't care or like Game of Thrones. These are kind of important characters in the network, and not just in the network, in the series. And let's see how do they evolve during the 5 books. Here we have three very interesting characters. So we see in the first book, Eddard Stark is on the top. No one can defeat him, and boom, something happened in the second book, and then Eddard Stark pretty much dies into oblivion. Then we see Tyrion Lannister. It starts off in the middle, and it kind of dies of a slow death, but I mean, why? We don't know. But I mean, this is according to networks. And we see there's a very stark increase from 4th book to 5th book for Jon Snow. And maybe, just maybe we know that. Why? So let's just create this set of characters. So basically these characters, so this very evil looking code, what it does is basically take out the top 5 from each book and give you an intersection of that. And these are the set of characters. We have Arya Stark, we have Catelyn, Daenerys, all the biggies of Game of Thrones. And now the exercise is to plot the evolution of these characters. I believe you already have the code for set of char. So and repeat the same thing for betweenness centrality too. This is degree centrality, not weighted. So and we have this evolve df data frame, which we created for degree centrality, like right here. So have a look at that code to do it for betweenness centrality too. This is for degree centrality. If you end up with something like this, please do this. Did you do for betweenness too? Maybe you'll see something interesting. Maybe. People who got this plot. Okay. And the betweenness centrality plot. So if we try to read this, it's in the fifth book we have this is Jon Snow, this is Daenerys. In the fourth book we have, I don't know, I think this is Arya Stark and Jaime Lannister of everyone. And so this is not very easy to read, but it kind of gives us a picture about the evolution of importance of a character over the series. And we all know who this person is, green, first to second book. So, and we do this for betweenness centrality, and we have something interesting here. Who is this fella? In the third book, kind of important, like important. In the fourth book, very important. Fifth book, what's wrong with this person? Why is this person so important? So, as we see, this person is Stannis Baratheon. People who are not familiar with Game of Thrones, I'm again sorry. So, can anyone think of a reason why? Why is Stannis Baratheon like not in given you don't have any knowledge about these characters? Why is this person very important? What could be a reason? No, but this is for betweenness centrality. This is not degree centrality. Given we don't know anything about yep, yeah, but why is this? Why is this? There's such a big difference between these things. Maybe. So, as we discussed in the last one, we have something like it's if you remember the barbell graph, it's possible that even though a node is not connected to a lot of other people, it could be important, and that's the whole definition of betweenness centrality. So what my theory is something like this: that Stannis Baratheon is something like node 5 here. It's like it's holding together two different families in Game of Thrones. Now maybe it makes more sense. So that's why it's important in this network. And if you see, it's not like it's just important in the betweenness centrality measure. It's also important in the degree centrality. But if you look at the degree centrality of book 5, it's Jon Snow, Daenerys, and Stannis, and there's not a lot of difference between them. But when you look at betweenness, there's a stark difference between the first and the second one. So just maybe it tells us something about the relationship of these characters in this network. And just because Jon Snow has the most number of connections, it's not exactly the most important character. Maybe not. We can debate on that. But according to betweenness centrality, Stannis is also pretty important, because if you remove this node out of the network, you're gonna break apart the network. Like these two different factions of this network are not gonna talk or fight, whatever. So let's once we know who is important, what is important, now let's introduce a new concept called communities. So Eric touched a bit on this, but and we're not going to go into the maths of it. And you have this nice bit of code written for you already, and we're just going to look at the output and try to understand what's happening. So in this part, what we are trying to do is we are trying to recreate the initial image that we saw, and every node is a color. Every node has a color which is related to its community. It's like orange. People in orange are part of a community. People in purple, blue, yellow, green are part of their own communities. But how do we get these communities? Again, this is a very active area of research. There is no correct answer of this. What we are using in this is called Luan community detection algorithm. The basic idea behind that is there's this metric called modularity of a network. The basic idea behind this is that you need to increase the modularity of this network. And how this works, I'm not going to go into the details of it, but the very basic idea is you start with, suppose there are n nodes in a network, you start with n communities. then you just start jumping around. Like suppose you go at node 1, and you're going to ask all the other communities that if I add this node to that community, will it increase the modularity of the network? If the answer is yes, you join them. And you keep on doing this, and you'll end up with something like this. And the good thing about this algorithm is it's very fast, it's really optimized, and I think it's n log n. And other algorithms who try to find communities in this are not that fast. And again, this problem is not well. It's not exactly well defined, because everyone has their own opinions about what's a community. So we're going to look at a very basic opinion that I think pretty much everyone agrees on. That is looking at the density of it. These are the communities in our network. Like we have, it's a dictionary which is keyed by like integers. So we have 0 community, 1 community, 2 community. And so let's draw a community out of this network. So we see a lot of connections, right? It's kind of dense. So maybe then by looking at the density of local connections, we can tell something about its larger macro structure. So let's look at another subgraph, which is a community according to this algorithm. Again, we find something dense there. So if we calculate the density of the full network, it's 0.03, and that's not really a dense network. And if we try to find the density of the community, it's 0.19. That's like almost 5 times denser than the actual network. Again, this is only it's one of the thought process of finding communities. Then there's this other area in which you try to find communities using flow diagrams. Not flow diagrams. It's like if you suppose the edges are the edges are pipes, and there's liquid flowing in everything in all these pipes. The idea behind that is, can we find areas which have similar flows? Maybe those are communities. Like these are different ideas out there, but I like this one. It's easier to explain. It's easier to understand. So, and this follows the idea of density. So, time for an exercise again. In this, we have to find the most important node in that partition. By partition, I mean the community, according to degree centrality. And if you're done with that, then according to Betweenness centrality. Once you are done, yeah. Oh, yeah, that's the thing. That it's nothing is right or wrong. It's that's the same thing with centrality measures, right? There is no wrong measure and there is no right measure. It depends what you want to find out. Yeah. I yeah, like Network X has flow centrality, but I have not really used it. But it has pretty much all the standard algorithms that you can find in network analysis. Is anyone else getting that error? Are you using Conda or pip? Can you look at the version number of this thing? Is anyone not getting an error? Sorry? For? Uh, okay. It shouldn't be 1001. Let me check. Are you using Conda or pip? Is the version number 1.0 or 0.1? Wait, did you install community or did you install Python Luan? Python Luan. Yes. Community is a different package. You should. Sorry about the mix-up, but you should do pip install Python Lua or Conda install Python Lua. It's community. Yeah. You're looking for this thing, Luan community detection. It's not zooming in. Yes. Is anyone done with the last exercise? So let's look at the solution. It's pretty. It's a pretty straightforward solution. It's like try to find the maximum in the partition. So if we combine these names with this and present it in a prettier picture, we'll end up with this. And for this, you need Kefi. So it's so this was Game of Thrones. Any questions? Any ideas? This is like we are done with the theory part of network analysis and using network X. So if you want to go on a tangent because you have the data, you have the notebook. If you want to go on a tangent and not follow the tutorial, that's perfectly fine too. If you have an idea of looking for an interesting thing, feel free to shout out, or maybe we can do that together. Any?
I have what feels like a really silly question. Actually, the variable D, the set, what does D stand for?
It's bad programming practice. And that's on me. Eric, when are we supposed to break for? Oh, yeah. So we have a lot of time. Any questions? Do you want to move to airports? How many of you flew in to Cleveland? How many of you did not fly? So let's open the 8th notebook now, which is about US airports. Again, you have to do the student one, but if you're too tired now, it's okay if you don't want to do it. So let's load in the data set. Let's have a look at the data set. Does anyone want to explain me this data set? So we have a CSV file which has year, and just neglect this column, which has year, origin, destination, unique carrier name, and passengers. And so basically this data set is from 1990 to 2015. So we have like a good amount of data for 25 years. And this data set is, it's basically about flights between airports. So if there is a flight between Cleveland and Chicago, there's information about that in this data set. And this is a very used data set. I have compressed it a lot and created a meta data set out of it, So this is the total number of passengers that flew in that year. So in 1990, from origin ABE, these are the ITA codes. From ABE to ACY, 73 passengers flew, and this is a set of airlines that operate on this route. So this is our data set. So what kind of network should we make out of this? It should be a graph, a directed graph, a multi-graph, a multi-directed graph. Yep. Yep. What kind of graph should we have? What should be the nodes? What should be the edges? Any ideas? Yep. Airports could be nodes. And what about edges? And what kind of edges? Do we need them to have direction? Can they be undirected? Do we need to have multiple edges between two airports?
What are we trying to evaluate?
We just want to model this data set. We have this CSV file. I am asking you to model this on a network. How are you going to do? Sorry? Right now, we're not looking for anything. We're just trying to model this into a network. Yes, there's one way of doing it. But what about year? We have like 25 years. So how do you want to encode that information? Yep. 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 That would work. And that. Yep, that's essentially a multi-graph. Yep. So there are multiple ways of doing it, and usually what I did was I just used the carriers. It's like different carriers have different edges, but I finally decided to, and I used to just work with five years of data set, but I thought that maybe no, we have 25 years. Let's just work with all of them. So in this notebook, we're gonna make 20, like if there is a flight, 25 edges between two airports, which is where every edge represents a year with attributes unique, like the carriers and the number of passengers. So how are we gonna do that? So NetworkX, the powerful library that it is, it already has something called from pandas edge list, or like it used to be data frame, but from 2.1, I think it broke apart and it's called now edge list, because this is essentially an edge list where like every row is an edge, where like origin and destination is the source and target of that edge. So we pass in this and create a graph called passenger graph with source as the origin, target as a destination, and attributes as the year, passenger, and the unique carrier name. And we create it using a multi-directed graph. It's going to take time because I think it's 500,000 of row. Let's see how big our data set is. Yep, it's 457,000 flights. Not flights, number of routes aggregated which are grouped by years. So like if you look at the original data sets, it's around like 22 million flights. So, and that data, if you try to load in that data set into this Jupyter notebook, it will crash So that's why I kind of aggregated some data, the data to get a nice data set that we can use. So I'm gonna take this flight, Cleveland to Chicago on Sunday, and I'm interested in looking at the history of this flight. So how many passengers usually take this flight. So this is one of the ways of accessing that edge, because in network X it's the data structure is basically a dictionary. So suppose you wanna okay, so people who don't know, CLE is the code for Cleveland. So this will return me a nice big thing called adjacency view, which is essentially a dictionary, which is keyed in by the destination airport. And if I want to fly to Chicago, I do this, and this will give me again an atlas view, which is essentially again a dictionary, which is keyed in by a new edge. This is a multi-graph. That's why we have multiple edges, which are keyed by from 0 to 25, where 0 is for the year 1990, and 25 is for the year 2015. We can see that in year 0, it carried around 386,000 passengers in the year 1990, and there were like 3 airlines: Continental, United, and American. One of them is not there anymore because of a merger. And if we see in 2015, there are a lot more airlines, even though there's not a very big increase. It's 400,000 people. So let's actually see the evolution of this passenger traffic on this route from Cleveland to Chicago. We see a very random distribution. By random, I mean I can't really think of any reasons of what's happening here. This is, I think, the 2001 is, you can attribute this to the terrorist attacks, because if you look at the bigger network, like the full network, and if you look at the flow of passengers, which is, I think, in the original data set, it's by month, you'll see this steep drop. I actually have that picture. Let me show you that. It follows a very interesting cardiac rhythm. Yep, this is if you plot the total number of passengers over the last 25 years, this is what you get. And you can see it's kind of increasing, and then in 2001 it suffers a major drop, and then it goes back, and then there's a drop in 2008, I guess because of the financial crisis. And the more interesting part is this cardiac rhythm. This is by month, so it's like every year there's a similar pattern. I've not really looked into it, but I think this is kind of interesting, and it would be a nice. It would make a nice blog post of why and what is happening here in these cardiac rhythms. And coming back to our notebook, so I mean, I can't really tell what's happening or why there's a fall, why there's a rise. This is just the data set. So let's do an exercise on this. The exercise is to find the busiest route in 1990 and in 2015, and plot the time series of the number of passengers on these route from 1990 to 2015. You can use network X to do this, and you can do just the pandas data frame that we loaded initially to do this. If you're gonna do it with pandas, it's gonna be super fast. So tread carefully. And if you have any doubts or questions, feel free to ask them. And once you are done, shout out the most busiest student 1990 and in 2015. Sorry? Yep, that's for 1990. And for 2015. For 1990, we know it's from Los Angeles to Honolulu. Anyone for 2015? Sorry? Yes, it's Los Angeles to San Francisco. Anyone trying to do this using the network itself? People who have done, people who have gotten the answer LA, Honolulu, and LA SFO, can you also plot the evolution over the 25-year period? Like, check out if anything weird happened with that route. Has anyone successfully done this with network, not data frame? Okay, so let's look at one of the ways of doing this. People who are trying to do this with the network, I appreciate you, but because of the structure of this, the data structure behind NetworkX, it's like you're essentially trying to get into a dictionary of a dictionary of a dictionary. So a lot of for loops to get this information out. But luckily, we have this information in tabular format, that is a data frame. So you don't really need to do that. So it's after a bit of pandas magic, we end up with this. So we see in year 1990, it's Los Angeles to Honolulu, and we have like 1.8 million. Yep, 1.8 million passengers. Like that's a large number of people, and LAX to SFO is 1.86 million. So like even in 24 years, the number hasn't really changed that much. But when you look at the evolution of this route from LA to Honolulu, there is a very sharp decline. It pretty much goes from 1.8 million to like I guess 1.1 million. I have no reasons for that. Anyone wants to speculate any reason for that? Yep. Yep, that would be a pretty good reason. You know what? We can make an exercise out of this. Yeah. Yeah. Yeah, let's check out. Maybe SFO is also a decline. So maybe let's see Seattle. It's not a stark increase, but oh, but it's like 80,000 people. It doesn't really make a difference. Like it lost 800,000 just from LA, so 80,000 can't really do anything. Let's check out from Chicago. Nothing out of this thing. So well, I guess this will remain one of the unsolved mysteries from this notebook, or yep, we can do that. Let's so this is for So what we care about is the number of passengers. I mean, there is a decline, but and from 8.9 million, we ended up at 7 million. So maybe Hawaii is not cool anymore. I guess that's a valid answer for this. Is Are there any big airports in? I'm not aware of it. does anyone know the IATA code of that? Let's see. For what? IATA, I think. Yep. Are there any other airports in Hawaii? Anyone? Sorry, what? OGG. So, I mean, yeah, OGG had an increase. It went from 2.2 to 3. So, maybe OGG is a more hipster place to be, not Honolulu anymore. It went from 1 million to. So, again, so from our last 6 minutes of research, we cannot really tell, we can't really conclude anything about the Hawaii tourism industry. So let's move on to the next one. So the second route was from LA to SFO. And let's see, this was the, sorry. Okay, this was the busiest route in 2015. Let's see what was its history. Okay, so I'm gonna theorize something here. You feel free to give me a rebuttal on that. This is the time when the .com bubble burst. I'm just putting it out there. I mean, if anyone has a better explanation, or even anyone wants to contradict that, then feel free. So this is from LAX to SFO. Let's see the other way around. Does it follow a similar thing? Oh. Please. I mean, come on, seriously? You're going to stop working after 4 years now? SFO to LAX. Yep, so it's a similar thing. I mean, this is something that you expect. Like, generally, if a plane flies from SFO to LAX, I mean, you can kind of say it's gonna fly back too. So yeah, that makes sense. So let's calculate page rank. So, whoa, we have a error in this. The error is that it's not implemented for multi-graph, and the thing that it's non-implemented error because it's not implemented. It's not like it's not possible to calculate for a multi-graph. It is, but it's not yet implemented in Network X. So if anyone wants to do it, feel free to do this. It's a nice activity. So. And the reason that we weren't working, like in the last notebook, we created 5 different graphs is this. Like, so suppose we want to extract a network out of this big meta graph, the multi-graph that we have, we need to write like helper functions like this to extract the 2015 network or something like that. So we extract the 2015 network, and let's check out the number of airports and the edges. So we have like 1200 airports in the 2015 network and 25,000 edges. So it's like it's not 35,000 flights. It's not 25,000 flights. It's 25,000 routes over this network. So, and because these are geographical points, we have GPS coordinates too. Sorry. So let's load in that list. You have all this code available, so you don't really need to worry about that. We create a position dictionary. And okay, disclaimer about this is that we have 1200 airports in this network, but we have positions only for 371. I don't know the reason why, but the data set that I downloaded didn't have information for all the airports. So we have information about only 371 airports in this network called pass 2015. And so what the exercise now is to plot this plot this network using coordinates. And how you gonna do that? And for that, we're gonna do nx draw. If you look at the signature, there is something called position. And it takes in a dictionary, where dictionary is this, which is called the position dictionary. It will, so basically the key is the code of the airport, and it's for the value is a two tuple, which is the latitude and longitude. So the exercise is to use this dictionary and plot something like this. Don't cheat. And if you try doing nx, so if you try doing this nx dot draw pass 2015, comma position is equal to post dict, it will throw an error because we don't have positions for all the network, all the nodes in the network, all the airports in the network. One way of dealing this could be like give them a dummy location, but that we won't do that. Instead of that, we'll learn a new thing that's called a subgraph, and you have to use that. And to use a subgraph, we do nx dot subgraph. You pass in the bigger network, and you pass in a list of nodes that you want to create a network out of. It will maintain the edges between those nodes, but it won't maintain edges like outside those nodes, outside the list of nodes. And you have to just draw the nodes right now. You don't have to draw the edges. And to draw just nodes, it's draw network X nodes. It's written in the hints of the question. And make sure it's not a disconnected network. Like there shouldn't be components of people talking. So if I give a message to him here, it should reach till Eric without him shouting to him. Or people who are familiar with scatter plots can do this without using all this network X fancy API thing. You can just scatter those points. But once you have done this, what I want you to do is just play around with this attributes. It's like you have something called node size. You have alpha. Alpha is like the how transparent the node is, and you have node color. It's like let's make it red or green. We have green. Let's make it something like 30. No, let's make it 300. Yeah, we have a dirtier network. Okay, can anyone? No, I think you can tell. But why do have these? Why this is the U.S. domestic network? Then why do we have these random nodes here and there? Like this is Alaska. This is mainland U.S. This is Hawaii. We have something here. We have something here. Can anyone theorize why? Sorry? Nope. These are US territories. Like if there's a flight to Guam or US Marina Islands, it's considered a domestic flight. So that's why you have these nodes to in the domestic network. There's going to be break in a minute, so let's just look at this. If we add edges too in this one, we're going to have something like this. Again, this is still prettier than what you will get if you just do nx.draw this graph. Let's try doing that. If we do just this, see, this is how slow this is. So basically, we'll end up with something like a hairball that we saw earlier. And again, this is not the best representation of this, but again, this is something. So when you can kind of make more, like, more pretty representations too. But like, I wanted to create the world. I wanted to map the worldwide sister city network. So like, anyone who knows what are sister cities. So like, if you open a Wikipedia page of any random city, there will be a column called sister city of that node. So what I did was I scraped Wikipedia to get this sister cities relationships, and I ended up with this network. So this nx.draw has kind of crashed my computer. It has seriously crashed my computer. But the lucky thing is, it's time for break. So I can fix this, and you can go have coffee. Sorry? That's nx, sorry, that's draw network x edges. more minutes. Any questions? Any insights till what we have done? So let's back. Let's get back, and we saw this scatter plot, which is basically uh, the plot of of airports in this network, and this is a somewhat pretty plot of the network itself. it's not the full network. It's 2015 networks for which we know the GPS coordinates of the airport. And so, what about the degree distribution? Again, we see something like this in a real world network. So I guess this the Barabasi-Albert model, after the whole reason it was created was of this, that you do find something like a, this is, I mean, like if you try fitting this to an actual distribution, it won't work, but it kind of looks like power law. So when I say it follows power law, it's a very wrong thing to say, but it no it kind of follows that that pattern. Again, if we plot the log normal plot of this, it kind of follows a straight of a straight line. Again, it's not perfectly in that distribution. So this is the 2015 network. So let's take a slight detour and talk about directed graphs. And we used PageRank once or twice, but we never actually talked what was PageRank, like other than the Google algorithm. So has anyone seen this picture before? This one. Can you tell what is it about? Yes, this is a pictorial representation of PageRank. So the name Page is from Larry Page, one of the co-founders of Google. So suppose we only knew the way of measuring importance in a network was degree. If we just knew that, then according to that, which is the most important node in this network, just according to degree. And because this is a directed network, let's talk about in degree, which is the most important node in this network according to number of the number of incoming edges. Anyone? B. We have 1, 2, 3. We have 6 incoming edges, and B is, according to our degree centrality definition, B is important. Well, I guess we can see that, but like the percentage here is the importance percentage in the network according to PageRank, and PageRank also tells us that B is important, but we have this curious case of C. C has only one incoming connection. Even after even with only one connection, according to PageRank, this is important. Can someone theorize why? Sorry? Yeah, maybe, but and yeah, I mean, yeah. I guess you can. Yeah, you can put it like that, or you can say something that if an important node is pointing towards another node, just by that link, in this case C has an incoming connection from B, and just because of that incoming connection, C is itself very important. So okay, so let me give you an example. Suppose you want to you Google which is the best programming language in the world. If you Google this, it's going to be a bunch of blog posts. So, but which one should, let's actually Google this. Let's Google this and let's DuckDuckGo it. Come on, please internet work. The internet's not gonna work. Which is like the first link, non-ad link. Which is the first word, Python or Java or? Okay. So like coming back to this, not this paper. Coming back to this, so suppose you Google which is the best programming language, And let's suppose a lot of people are writing blog posts on this. So if person A has person A writes Python, person B writes Java, person C writes Ruby, or person D writes or like C, C++. Like Google has indexed all of this. Like, it knows that person A said this, person B wrote a blog about this, person C. How it's going to rank them? Then the basic intuition behind that is you go one layer back. You see who all are pointing towards person A's blog, who all is pointing towards person B's blog. Suppose the website from a well-reputed engineering tech company cites person A a lot, and some people from the financial industry, which do a lot of tech work, a person, they also cite A, B, and C, and there is no one actually citing D. So suppose Python Software Foundation cites person D, and no one else is actually citing person D. So, and according to the importance of these one, you go one layer back. So this is the basic intuition behind that, and how important important nodes are pointing towards that node. At the end of this, this is at the end of this, you get this fancy looking algorithm. It's not actually very fancy. It's like very basic, not basic, but it's an interesting bit of linear algebra. If you're interested in it, you should go through it. And just a bit about directed graphs before we go back to airports, because they are directed networks. So when we create something like when we call the digraph object and we add an edge 1 to 2 with a weight, let's say 1, the difference is something like this. I'm just showing this to make you understand the difference. So if we do G1, it will return me a dictionary. This is one of the ways of accessing the data structure. If we do G1, it will return me a dictionary view, which will give me a list of nodes it's connected to. So G1 will give you 2, and if I do G2, it will give me an empty dictionary, because there's a connection from 1 to 2, but there is no connection from 2 to 1, because it's a directed graph. So this is one thing to keep in mind. So coming to this again, suppose we create this network in which it's kind of like a star network. By star, I mean all the nodes are pointing towards. In this network, all the nodes are pointing towards 2. Wait, do you see curves? Oh no, that's the this thing. So everyone is pointing towards 2. Like you have 3, 4, 5, 6, 7, 1. And if we look at the in degree of this, in directed graphs, you have degree, which is essentially in degree plus out degree, but it's not the best thing to look at, because we know edges have direction, and when we just look at the degree, you are saying that we don't care about that information, and that's wrong. You should care about direction of edges. So in this in degree, we see that 2 has an in degree of 6, and every other node has an in degree of 0. If we look at the out degree, then we see everyone has 1 and 2 has 0. And if we calculate the page rank now, like as we discussed, everyone is pointing towards 2. So 2 has a very high page rank, which is like if you compare it with other nodes. So suppose we add an edge from 5 to 6. What would happen to page rank? Any guesses? And will anything happen to 2? Like not in numeric terms, but as we can see, 2 goes down, because apparently like 6 has some kind of more enforcement from 5. So 2 won't go up, but 2 will go down and 6 will go up, but still 2 is more important than 6. Oh wait, we went ahead. Yep. 2 is 0.48 and 6 is like 0.11. There's still a difference, but it's less now as compared to 0.5 and 0.08. So let's now create a new edge, and it's from 2, the central node, to 8. As you can see, this is the edge that we have added. Now what will happen to the page rank? Yes, but how up? Like, I mean, yeah, that's a fair enough guess, but like, the funny thing is, in this case, 8 goes more than 2. This is just a coincidence that 8 is going more than 2. It doesn't really say anything about this thing, but we see that 8 8 is 0.32 and 2 is also 0.32. So even with just one connection, 8 is a very important node because that connection is from 2. So this is not all you need to know about PageRank, but this is the basic intuition behind PageRank, and this is a very powerful and simple to implement algorithm. And if you're interested, you should definitely check this out. So let's go back to airports, and let's do the standard thing again. Let's find the most important node in this network, because we have been doing that for the past 5 hours now. So let's okay, and now we know PageRank too, so we'll do PageRank, we'll do Betweenness, and we'll do degree centrality. So the interesting thing, A and C, is anyone familiar with this code? A and C, according to PageRank, it's the most important node in this network. Like, this is the most important airport. If there is a natural disaster, or if this airport is flooded, it's not good for the network. Which is this airport? Anchorage. Surprised anyone? When I was first doing this, I was expecting something like maybe Chicago or Atlanta, or the usual big traffic airports. But why Anchorage? Yep. And yes, that's one of the correct, not the correct, I think that's one of the valid reasons that I believe is why Anchorage is this. But, sorry? Yep. So let's go back to the actual network representation. If we can't really zoom in, but if we try to look at this, you see that most of the airports in this are not connected to mainland through direct flights. They either go through Fairbanks or Anchorage. So it's kind of like if you remove Anchorage or Fairbanks from this network, you are breaking apart the network. But this is the this is the intuition behind Betweenness centrality. Why is PageRank telling you that Anchorage is very important? Any guesses for that? Again, we can look at this network. Yep. So again, for what my reasoning is most of the major airports in mainland US have flights to Anchorage. So it's like a lot of important airports are already pointing towards Anchorage, which will bump up its score. So that's why. Again, this is my reason. I'm just theorizing stuff. There's a nice blog post about this, which discusses a lot of things. And one thing to keep in mind, we are just looking at the structure of the network. We're not looking at number of passengers. We are not looking at number of flights. We are not looking at number of even cargo. We are not looking at that. We're just looking at the structure of the network. And by structure, I mean, suppose there's a node from even if there are 10 flights between LA and SFO, we don't care about that. We just care about that one connection. And this is and we have calculated PageRank Betweenness for unweighted right now. We are not taking passengers into account. We have the information of passengers, but we haven't. And we have ANC, Fairbanks. I don't know the third one. or the fourth one, fifth one is Denmark, then Atlanta, then Chicago. Then you get the usual ones somewhere in the top 10. But when I first did this, it was like I was like, wait, what's Anchorage? And if we do for degree centrality, because degree centrality takes in just the number of connections, you will get what you expect. It has Atlanta, Chicago, DFW, Denmark, and you still have Anchorage, but it's not at least on the top. So there's this blog post. It's linked here if you want to read more about this, in which they discuss different reasons for this. So again, till now we were just looking at the structure of the network. What happens if we add passengers? Because we have that information. Will that change? Let's see. See, this is Python. That's why it's slow. Come on. This shouldn't take this much time. Okay, the reason it's taking this much time is like when you're calculating betweenness centrality, how it's implemented in network X is they basically pick 2 nodes in the network. You calculate the shortest path in this, which is, I think they use Dijkstra, like that's the standard one. And I think it's n log, it's v log v, right? The complexity. And after that, they do this for every 2 pair in the network. And like suppose there are 1,000, then it's like 1,000 C2. And they try to find this, and then they take the average of it. So that's why it's taking a lot of time. And by the time I was telling you that it's done. So now we have Seattle as the most important node in the network, according to Betweenness, and Atlanta, Chicago, Seattle, according to PageRank. But still, Anchorage is there. So Anchorage actually has a lot of passengers that people who are going to Anchorage, and it's a very important node in the network. So we can conclude that Anchorage is kind of important. But again, like now we are happy because we are not wrong in our initial assumption that if someone asks someone which is the most important airport in the network, you won't say Anchorage, you'll probably say JFK or Atlanta or Chicago. And now we are happy because we see those results now. That's why I'm happy. So let's talk about something called reachability. I shouldn't use this term because this actually has a kind of different meaning in a network. So let's just use reachable in its English sense. How reachable is this network? So let's try to calculate something called the average shortest path length. So again, this is the average. This is the average jumps you have to make to go from one average jumps you have to make to go from one node in the network to the another node, and we get an error which is graph is not weakly connected. When we were dealing with only connected when we were dealing with only undirected graphs in the first part, we saw connected components, right? So this is to give you let's draw it out. Let's create a random graph. Let's create 10 node and 0.1. So we can see there are 4 components in this network, right? If you are stuck here, you cannot go to this component. If you're stuck here, you cannot go to this component, and that's the idea. But this is again an undirected network. So what is weakly connected and like naturally strongly connected? So let's have a look at that. So if we try to find the weakly connected components, and the thing is that this is a bad thing. So this is what exactly this is what this means, that there are let's not talk about airports. Let's talk about, suppose this was a road network. There are cities out there which are not connected to each other in a country. Like, given, let's suppose there is no, geographical limitation. That's a very stupid thing to do. You should be able to reach from one city in this airport network to another city. So why is that case? So let's look at weakly connected components, and we'll get to what the difference between weakly and strongly a bit later. Sorry. Even if they're regional, they should be connected to some big right. Otherwise, suppose Alaska was not connected to anything. How am I gonna go to Alaska? I want to meet the bears. So we have three. This is the one. There's this one big component which should be actually one component, but we have three components, and one is the usual one. The second one is something called component between SPB and SSB, and the third one is AIK. So this is only one node in itself. So apparently there's a flight from AIK to AIK. I mean, what that means, I have no clue. So basically, if you this is that flight. This is for 2015. There's this airline called Right Air Service, and this is an actual airline. It's not it's not an airline. It's a charter airline. But I have no clue what these flights are, and these flights are not joyride flights. It's not someone came and oh, I just want to go around and come back. These are properly either licensed, either scheduled or unscheduled charter flights. So these are proper flights. Yeah, that's yeah. So, but that data should not be in the FAA data set. So, because we don't know what AIK is, we're going to remove it from our network. So the curious case of SPB and SSB is we have solved that case, and so basically that's it's a seaplane company. So these are two seaplane airports. They just fly to each other. So yeah, I mean that's okay. That's not really stupid. So but still we don't really care about that. So we're gonna remove those nodes too. It's gonna make our life easier. So is this network weakly connected? We get true. But this is not strongly connected. So what do we mean by strongly and weakly connected? Let's have a look. So suppose we have a directed network like this, which is basically there's a node from 1 to 2, 2 to 3, 3 to 1. If I place you anywhere on this network, you can reach any node. Even though there are directions, you can go from 1 to 2, you can go from 2 to 3, you can go from 2 to 1, basically jumping around the network. Suppose I add a new edge, 3 to 4. But as soon as you reach 4, you cannot go back. Suppose I drop you at 4, I'm come back if you can. You can't. So this is the basic difference between strongly connected and weakly connected. If this only matters for directed graphs. So if a network is strongly connected, then you should be able to go from one point in the network to another point with taking direction into picture. You cannot just forget direction. But if you want to just see the undirected version of it, if you just disregard direction, if you do this as weakly connected, then you're gonna get true, because if you're checking for weakly connection, you're just checking that is the undirected copy of this graph connected. So that was weakly and strongly. So, but again, an airport network, in my opinion, not in my opinion, I think common sense should be strongly connected. So if we try to run this, try to find strongly connected components in this network, there are some airports in which you can just fly to. You can't come back. I don't know what this is. Or there are some airports from where you can fly, but you cannot. You have to take the train or bus, something, to go back. So suppose so you see a lot of the components of length 1. These are the components, and you have like one big component which is the, I guess, the actual network. So if we look at some random node from the one component, so it's like, you know, in year 2015, if there's this airport called TSP, you can only fly to this airport. That's kind of crazy. I mean, so let's take another. Let's say E key. Sorry. I mean, what kind of prison is it? Maybe, you know, people should go back. So there's this origin destination HPN to AKI. There's some carrier which carried 5 passengers there, but those 5 people are not to be seen anymore apparently.
I think ERA is for real airports, but with a specific purpose. So it was kind of shipping things for them.
No, but these are people. I mean, these are not objects. They have feelings too. Okay, so let's create a new graph. We'll call it Passenger 2015 Strong, which is a strongly connected network for the year 2015. Let's check that out. So even after, you know, discarding all the useless or whatever special nodes, we end up with 1,190 nodes. So yeah, it's a big enough network. And now let's calculate the average shortest path length. And because we know that it's connected now, so we're gonna get an answer. Again, this is gonna take time because it's calculating shortest path for all the pairs. But as we saw the answer before running it, it was 3.14. So what does that 3.14 mean? 3.17. So this number signifies that you can jump from one airport to another airport in 3 jumps on average. The worst could be, let's check out the diameter. A diameter of a network is basically the longest shortest path in a network. It sounds funny, longest shortest path, but that's what it is. And I think this is going to be slow. So till that is running, we're gonna do this exercise. And the thing is that if you are successful, if you are able to solve this exercise successfully, you can make a lot of money too. So the question is, we have this network. There is only, and you have to add flights to this network, irrespective of thinking about, like, you know, is it going to be a sound investment or not? We are doing this for social good. And the aim of this game is to decrease the average shortest path length of this network. And the rule is you cannot add more than 2% of the current edges, that is 500. So you can add 500 new flights in this network. Right now we have Right now we have 25,000 flights, like not flights, but 25,000 routes. You can add 500 more routes, but you have to decrease from 3.17 to something less than 3.17. And the diameter is 8, so that's the longest, shortest path. So, and again, I have no clue if there is any correct answer for this exercise. I'm pretty sure this is a very tough optimization problem, but well, you know, so I'm gonna tell you my this thing. It would be nice if someone can beat this. I'm probably sure you can beat this by maybe, you know, getting random nodes or something, random flights or something. I got 3.008. And just to give you an idea what I did there, I think even you have similar code in your notebook, but it would be better if you can, you know, come up with something new, if that works for you. So my basic idea behind this is I sort these all the airports according to, like, you know, decreasing order of degree centrality, and then I start picking up nodes which are not connected, basically in this order, and I add the first 500 edges that I can make. This is my idea behind this. and I end up with 3.08, we have all the time. Can someone do anything better than this? We have, we're gonna do 10 minutes for this. The one who gets the lowest wins a prize, and that's gonna be a surprise. Instead of looking at just degree centrality, I looked at page rank, the fancier one, and I was able to beat myself from 3.08. I went to 3.03. Yeah. Let's see if this. Let's see if betweenness centrality makes a good difference or a bad difference. Before running a new strategy, make sure to create the graph again, because you have already added nodes and you're adding more nodes, so that's cheating. You can only add 500 new. You can only add 500 new edges. So make sure you create this graph again by this thing. You can copy that from line 63, but that would be something different in your notebook. Yes, I beat myself again. It's 2.97 with betweenness centrality. If you do the same thing. So reigning champion is 2.97. Can someone beat that? You don't actually have to code. You can just throw some ideas what you're thinking, how to decrease the average shortest path length. Yep.
So essentially, you're trying to, like, the leaf nodes are going to be the ones with the longest distance to each other, probably. So if you
So basically, what you're saying is like we can start looking at the diameter, and instead of find the nodes with which has the longest shortest path lengths, and then join them. Okay, that would work. In this, there are 1,200.
So then find all the airports that don't fly to New York and connect them to New York.
How will that?
Because from New York you can probably fly anywhere. And so then if you just try and decrease the shortest.
Maybe that will work. If you code it, and if you get a better answer than this, then that's the winner.
I think it's
Oh. You can code.
Connecting all the airports in Alaska.
Sorry.
Just connecting all the airports in Alaska, like to each other, instead of through Anchorage or Fairbanks. Because Alaska, on the map, Alaska looks a lot smaller. That's also a distortion. So, in reality, Alaska is massive. And a lot of the airports up there don't connect to each other.
I mean,
They connect through Fairbanks or Anchorage.
yeah. I mean, yeah. You are decreasing the average shortest path length from the airports in Alaska to mainland US. Yeah, that could be a strategy. Again, these are hypothetical routes that we are planning. We're not going to solve aviation industry's problem here. Like that solution is, I think it's a very good solution, even though it's kind of unreasonable. But it will it will probably pass this metric that we have come up with, like average shortest path length. Is anyone trying anything different or crazier than this? Okay. Okay. Yeah, that would definitely work. .97 is our current champion. You have to beat that. Any more ideas regarding this?
Now, given that the total number of nodes is only 1190, you can just take whatever airport has the most different edges and say randomly add 500 more different airports connecting directly to that airport.
Yep. You know what? Let's try it out.
You're going on 2% of the edges, not 2% of the nodes. So just make somebody act like Google.
Yep. That is the plan. The highest degree was Atlanta, right? So what we're going to do is Ooh, that's close. 2.98. No, it's kind. It's so basically I'm trying to connect all the nodes that are not connected to Atlanta to Atlanta. Yeah. Yep. And yeah. And if we do the other way around, it's like instead of flight from Atlanta to yeah. If we add a flight from Atlanta to node, it's 2.98, and if we add a flight from node to Atlanta, then it's 2.97. Yeah, yeah. Yeah, we can write a grid search to find the best one. Yep. Okay, but this is a nice fun exercise. Everyone can try this at home maybe, or if you have any ideas, feel free to shoot them to me. And if you beat 2.97, then please let me know. Sorry. Sorry. Yep. UCL. Oh, Seattle. Oh, sorry, what? Oh, yes, I have to change Atlanta. Now, maybe this could be a nice answer too. Okay, let's move on now. So, right till now, we are talking about passengers and airports. Now, let's talk about airlines. Like at this very moment, I'm very, very pissed with United for different reasons. Last night, my flight got delayed by 6 hours. I was supposed to reach at 10 p.m. I reached 4 a.m. in the morning. That's why I'm very grumpy and seriously sleep deprived. And so the aim of this part is to find something interesting / embarrassing about the United Airline network, so we can tweet to them and like, haha, gotcha. If we can do that, that would be really that would make me really happy. Okay, so Seattle is not a good thing apparently. Seattle is not working. So continuing with United bashing, and they also debited my credit card for Wi-Fi, and I didn't get Wi-Fi, so I'm angrier. So yep. So in this we create a airline network that's specific for United Airlines. So there's a bit of an issue with this data set. It's like when we look at the data set that is pass air data. When we look at the list of carriers, it's a list of carriers, but it's actually a string, because when you have like a set or list in as a value in a column in a data frame, and you dump it, it dumps it as a string, not really a list. So and when you read it, it's reading as a string. So to rectify that, I came up with a very shitty way of doing that. So I mean, this works. So it's shitty, but it works. So I don't care. So like, this is how it works. It will give you a nice list of airlines, and we create a passenger graph. We create a new attribute airlines to store this list of strings of our airlines. So the exercise it's to create a network, to extract a network out of this network of the 2015 year, and create it only for United Airlines. Then make sure it's a weighted network. By weighted, I mean make sure it has the term passengers, and find the size of this network. Just not all the routes that there are, but just United network, and find the most important airport according to page rank and degree centrality. And just for fun, we're gonna compare these networks with the actual hubs that are of Atlanta of United that they claim. You have 10 minutes for that. I'll be there. When did you?
This morning.
How do you add one more?
Oh, I see. Escape A. Oh, do we want to pass air data and not passenger data? Let's see. Okay, yeah, pass air data. Probably need to carry them over there, but
That's
pass
the
air
original data frame.
passenger aircraft.
For what?
Is there a fix for that problem?
Passenger graph doesn't have it in there, so we need to do something. Add it. So the definition of passenger graph is what's missing.
Oh, but why is that? Why is the case?
Show us your definition of passenger graph.
You should have unique carrier name in that too. Let me check. So when we do passenger graph, you should have unique carrier name in this. Oh, I'm so sorry for that. Oh yes. I'm sorry. I think I didn't do that. I'm sorry about that. Just add a new. Yep. Did it work? Just let me know once it works. Yep, cool. So yep, perfect. So according to Wikipedia, United hubs are Chicago, Denver, LA, New York, San Francisco. We're gonna see if our data and network analysis tells us that too with this exercise. There's this weird string thing with the United Airlines thing. Just avoid that. Like don't worry about it. It's already there in your notebook. It will work. 2.97.
I got 232.
Woo. What did you do?
Alright, so I changed what I did, but I did PageRank, took the top 50 out of PageRank, then I went through the reverse sorted of the sort tree you had, and I said if the neighbor is in the top 50,
Okay.
use it. That way, because we have, like minimize the node count, right? And it was 3 was the set, so I need to make sure it took the next hop.
Interesting.
Try betweenness, maybe even better.
Yep. Try doing this with Betweenness. And instead of PageRank, to Betweenness. Ladies and gentlemen, we have a winner.
So I use betweenness.
Yeah, because betweenness you're going to identify the bridges.
Yeah.
So it means that those bridges, you need to go through those bridges to reach the rest of the graph. So once you identify the bridges and you add another edge from the bridge to something that was very far, you're connecting everybody.
Swap this or something.
I'm just gonna. Okay, so let's just look at the most important nodes in the United Airlines network. We find, according to PageRank, it's Chicago, not Denmark, Denver, LA, SFO, Washington, New York, and these are the actual hubs of United Airlines. So it works, yeah. And so this is just another exercise if you want to try it out. But so what we're basically looking at the passenger traffic out of Cleveland on United Airlines, and we see apparently there's a very big jump, and I think this jump is because of the merger between United and Continental. I think, I'm not sure, but maybe. So, and we're done with the airports data set. If you have any interesting tidbits or, like, as I said, anything about United that you find, please let me know. And now I'm going to hand over to Eric back, and we have 30 more minutes, and he's going to go through bipartite matrices.
Are we up? Everybody can hear me? All right, first off, thanks, Mridul. That was a short word. This is our first year actually teaching together as a two-part tutorial, right? And so today, second part, he's the star, right? He got all the stuff done, so it's amazing stuff. So great work, Mridul. So we left part one with me hurriedly rushing through matrices and trying to show you some interesting stuff and not getting enough time to do it. So thanks, Mridul. We have a chance to actually explore this slightly in a bit more depth. So we're going to continue back to matrices. All right, so if you could open up notebook bonus notebook number 3. There's this section on matrices. Now, we have new participants in the class, so I'm going to just very quickly give you an overview on, for the newcomers, what we mean by matrices and graphs. If you look at a graph, you can take a graph and look at its matrix representation, right? It's got a matrix representation, which we commonly call the adjacency matrix. The adjacency matrix is constructed by ordering the nodes somehow along the rows and the columns, and filling in a cell if there's an edge between that particular node and that other particular node, all right? So this is what we would call the adjacency matrix. If we come back to the top of the notebook, we left off with, the matrix form of this chain, this toy graph, which is just a linear chain of nodes, right? So nodes 0, 1, 2, 3 in that order. You'll notice there's no diagonal elements, and that's because we don't have any self loops. No nodes are connected to themselves. Secondly, all of the edges are filled as off diagonals by one matrix unit, right? So that is node 0 is connected to node 1, node 1 is connected to node 0 and node 2, node 2 is connected to node 3, node 1 is 0, 1, 2, node 2 is connected to 1 and 3, and node 3 is connected to node 2, all right? That makes sense? That makes sense? Okay, cool. So that's the matrix thing. And then I gave you a little bit of an introduction to the 2NumPy array function from NetworkX, which gives you exactly that, right? So if you look at what's going on under the hood in NXViz, literally I'm hijacking 2NumPy array and then using matplotlib imshow, right? That's all I'm doing with a matrix plot. So this is used behind the scenes in NXViz, and this is what we want to play with when we're talking about doing matrix math with graphs, all right? So now, just to quickly recap for those who are here, if you take the power of the adjacency matrix, you will get back the number of ways that you can go from one node to the other node. Yeah, exactly. You can in k number of steps. So if I take a to the power of 2, where k is now equal to, so adjacency matrix power 2, then just to recap, that is the number of ways that I can go from each node to another node in 2 steps. And if I take a to the power of 3, then that's the number of ways that I can get from a node to any other node to the other nodes in 3 steps. And the values inside this matrix will tell us exactly how many ways there are. So in this case, there's no way to go from node 0 to node 3 in 2 steps. Therefore, the second power of that matrix is 0. It's in 0 in these positions. There's one way to go from a node back to itself in 2 steps. You go there and then back. So the first node, the termini nodes, you can go one neighbor and then come back. For the ones in the middle, there are 2 ways, right? I go out and then come back, right? So this is just a quick recap for those who are there. And if you do the matrix power 2, it just turns out the diagonal is also the degree of each node. So let's see. If we have a directed graph, then we'll have an asymmetrical matrix. We established that earlier. And we can also, we do the exact same thing with directed graphs. We can find the number of ways to get from one node to another in k steps by doing the kth matrix power. All right? So if you all could do this, what I really would like to have you do is the message passing section. The message passing section is where we can get to make fancy matplotlib animations, all right? And have a little bit of fun over here. So we're going to skip all the way down, because that basic material I had covered in slightly more depth earlier on. We're going to do this message passing thing and go and do it with actually a real network. So now the message passing thing, now I can actually spend a bit more time in detail over here, because I think I remember we went really fast over this. So with message passing, the way that we want to model the messages being passed over the graph is by first creating a vector that represents the message at a particular point, all right? So for example, again, in this linear chain over here, if I have a message that starts at node 0 and is not present anywhere else, I can model this by creating a vector that has a 1 in the 0th element and zeros everywhere else. Is everybody okay with that? Everybody's okay with that? Good. So then if I take that vector and vector matrix, is it matrix vector or vector matrix? I think it's vector matrix, multiply it against the adjacency matrix, we'll get the result of message passing 1 step onwards. And so if we do this 2 times with the resultant matrix, we'll get where the message is. So convince yourself that this is exactly what's happening. Okay, so we have the message initialized at node 0. You can follow along in your notebooks. After 1 round of message passing, we get message 2, which is a vector in which now that 1 has moved from the 0th position to the 1st position. And if we take message 2, vector matrix, multiply it against the adjacency matrix again, suddenly in message 3, that message has moved to the 2nd position, to the third node, that's right. And so then you can convince yourself by, let's do this together. Let's do message 3 at A2, and it will be at the end. Right, everybody gets that? Okay. You should know this is a reason why you should be on Python 3. If you are still on legacy Python, and I refuse to name its version number, if you are still on legacy Python, you do not get this @ operator. All right? This @ operator was specifically added by the core Python team for the numerical computing people. Right? So it's designed for people like us. So use it. There's no reason you should be still on legacy Python. Okay? Great. So now what I would like you to do is to attempt the problem of simulating a propagation for k steps. Right? Let's write a general function that simulates the propagation for k steps. And what this function will help us do is it'll help us build the animation thing that we're going to see that some of you previewed in the at the end of the first part. Okay, so in this function, what I'd like you to do is implement the propagate function. What it has to return is a list of matrices, all right? The first element in that list is the state of the message at time 0. The second element is the state of the message after 1 round of message passing, and so on and so on and so on, up to the kth message, kth frame, right? N frames is the number of frames we simulate for. So go ahead, implement that. And when you're done, you can cross-reference your solution against what's on the screen, and if it looks roughly correct, give me a thumbs. Depends on how you do it. Yeah. So if I were to, so the question is, should the append occur before or after? If I had initialized message states with the message, then I would put the message states.append new message afterwards. So this is what I think you're thinking about. Right? You're thinking about something like that? Yeah. Actually, yeah, that probably is the better solution now that I'm thinking about it. And so we can actually get around this by taking that out and putting message inside there first. So if you have something that looks like this, that should probably work correctly. And I am going to double check. Yes, it works. Okay, there you go. If your thing works, if you go run the matplotlib animation functions, you'll get something like this on the screen, right? Christmas lights, flashing Christmas lights, flashing LED lights. Okay, how are we doing? Thumbs? Good, done? Yes? Okay, it's been a long day, I understand. If you didn't get it in time, don't worry about it, all right? Really, the magic is happening inside this for loop, right? The goal, of course, is we want to just get the list of states so that we can index into that list of states when updating the matplotlib animation. If you didn't get, if that wasn't clear, don't worry. Don't worry. The main idea is that we practice doing the matrix, the vector matrix multiplications. All right. That will give you this. And so now, let's do the rumor network from the data set that we've got loaded inside there. Right? So let's do the rumor network and initialize the message state with any node you want, and let's see what kind of different animations we get. All right. And for the benefit of you, for those of you who would like to see the implementation of propagate. I'll put it up on the screen. You can find it on the instructor version of the notebook as well. Looks like I should zoom in. How's that? So how many people have your animation working? That animation should take about 20 odd seconds to render and stuff. So it should be running for quite a while before you actually see it happen. Oh, okay. I've seen that error before locally. Are you on Jupyter Lab? Jupyter Notebook? I'm not sure what's going on there right now. We can debug that later. All good? All good? Okay, so yeah, that was just a little fun thing that will let you visualize, how the message is being spread. The core idea is if you want to model message spreading on a network, you do have to have the message state and the adjacency matrix present, and it's just a simple matrix vector multiplication. All right? All right, so then the other thing that I wanted to cover was this notion of projection. We talked about bipartite graphs. Very briefly, for those who weren't here in the first part, bipartite graphs are graphs like customer product graphs, where a customer buys a product. So their edges can only be defined, so there are two node sets, hence bipartite, two partitions, okay? And you can only have edges joined between nodes of one partition and the other partition. So the concrete example to anchor your idea about this is you can never have a customer purchase a customer, or you can never have a product purchase a product. You always have a customer purchasing a product, okay? So as it turns out, bipartite graphs have a very nice property. Let's say we have a very small toy graph, right? If you go down to this section over here, let's say we have a very small toy graph that is the purchase history between customers, 3 customers and 4 products. So we have a 3x4 non-symmetrical matrix. If we take the customer product matrix and matrix multiply it against the customer product matrix transform, what we'll get back is the customer by customer projection of the bipartite graph onto just the customer nodes. Okay? So we'll get back a square matrix that is customer by customer. And customers will be joined to one another in this graph on the basis of having shared purchases. So convince yourself that customer 1 and customer 3 share one purchase, right? Look back at the original matrix. They share one product. Customer 2 and customer 3 share 2 purchases, right? The first column and the third column, right? Make sense? Right? And here's the best part. The diagonal shows the number of products that the customers originally purchased. So it's the degree in the bipartite graph of the original, of that node set. So it's a very neat result, right? And you can get some very efficient stuff. So you can do the same thing with products. Just do the opposite. You take the transpose, multiply by itself, right? So you get the dimensions. If you get the dimensions done right, you'll figure out which one is, whether you're doing the one projection or the other. So in this final exercise here, this is a really fun one, which I want you to, this one is Amazon customers reviewing music, right? So it's almost like they purchased, although not really. All right, so go ahead, load that data set, run that cell down there, and implement the get partition nodes function, all right? And then use that to compute the bi-adjacency matrix of the Amazon customer product graph. This function, the by adjacency matrix, is the function that you need to take the graph object and to compute then a corresponding adjacency matrix. So there's a two-step process involved here. So go ahead and do that. And if you're too tired and you don't want to think about problems, the answer is right up there. No problem, all right? I totally understand. It's been a long day. You've been thinking about network science all day long. Go ahead and copy the answer if you don't want to do any thinking. And if you've chosen to copy the answer, just fake it and tell me you've completed the exercise anyways so that I know that we're at quorum, all right? Okay, let's just do a quick thumbs. If you've copied or finished, please give me your thumbs up. Okay, great stuff. All right. Basically, we're filtering the node set of the original graph to find those nodes from a particular partition. And you'll notice if I do get partition nodes, if I call on get partition nodes, it just makes my code a little more readable. Then, after that, we pass customer nodes into the bipartite by adjacency matrix. We pass in the Amazon, the graph object. And what the bipartite by adjacency matrix, what that needs is a list of the nodes from one partition so that it knows what to put in the rows, and then by exclusion, the rest go on the columns, all right? Row by column, node by node. That's how the adjacency matrices always work. In the case of a bipartite graph, we put nodes from one partition as the rows, and we put nodes from the other partition as columns. All good? So that's how we create that matrix. So likewise, if you do the customer matrix, right, you do mat, because the rows are customers, you do mat matrix multiply by the transpose rather than the other way around. And then we get the diagonal to get the number of products that they purchased. And finally, we can get the index of the customer that reviewed the most number of songs, all right? So the index is customer 294, and it's in customer 294 in the nodes list. And if we do the same thing by doing degree of each customer node, we'll verify that it is still 294. So we've got the same result, two ways, okay? Let's see. We can then, so I'm just gonna lecture at this point because I see everybody sort of like, I can't think. So okay, I'll just walk you through the code and the logic behind it. So, and the final part, the question that we're trying to do is find the two customers that are most similar on the basis of shared reviews. So this is like finding, based on the projection onto the customer nodes, which edge has the highest weight, all right? And this we can do with a matrix interpretation. So first off, what we need to do is we need to find, so if we use just the projected matrix alone, we won't be able to use some simple argmax kind of functions to find the index at which there's the maximum review, maximum value, because the diagonals are going to be huge. They're going to be huge numbers. They correspond to the total number of things that they reviewed at first. So we actually have to take that sparse diagonal matrix, subtract off the diagonals, and then only look at the off diagonals. By looking at only the off diagonals, then we can find the two customers that are most similar, rather than looking at how many reviews each customer made. All right? Make sense? Does this make sense? The off diagonals are always edges between different nodes. The diagonal represents stuff for a single node. Okay? So we have to subtract the diagonal first. So that's what we're doing here. And then we're finally using some unravel index and argmax magic to figure out that we're most similar between customer 294 and 86. Great. So, just to reiterate the last point that I made, at the end of that, we have the object-oriented, or pure Python way of doing all of this computation, right? We get the projected graph, the weighted projected graph, and then we find the most similar customers by iterating over the edges. As it turns out, most of the computation occurs in this line that I'm highlighting, line number 4. All right, line number 4 in that cell. It just takes a lot of time to compute that. Roughly, I don't know, in Mridul's computer, it's like 29 odd seconds. The bulk of it is occupied by doing that. The iteration over the edges is like trivial. So there clearly is a performance hit when we try to use the object-oriented way of doing things. So think about, whereas if you do the matrix thing, it's like 1 second. So what, it's 0.8 on my other computer. So we get like a 30-fold speed up. So what I want you to think about here then is like, are you going to optimize for speed, or are you going to optimize for readability? Sometimes you have to make a trade-off there when doing your programming projects. In this case, if we were really analyzing, graphs on the order of tens to hundreds of thousands of nodes, you will get a big performance boost if you can formulate your problem as some matrix algebra operation, right? So you can do your message passing rather than by simulating messages being passed node to node. We can just do the matrix multiply and very efficiently get our messages being passed and simulated. Okay, so any last questions? Time it magic. No, I just wanted to. If we use the time magic, it runs it only once, right? Oh, okay. I forgot to do that. I was just like stuck in like start equals time mode. That's all. Any other questions? All right. If we don't have any questions, thank you all for those who've been here for 2 parts, 6 hours and 40 minutes of network science. Kudos and props to you. Give yourselves a round of applause. Also, thank you for coming. Appreciate any feedback that you have. All right, thank you.